Hello, everyone. I'm Joshua Mack, and along with me is Serhan Ganer. And today we're going to be talking about GNURadio and CEDR, runtime scheduling to heterogeneous accelerators. And so for some background on who we are, we're part of a research collaboration between a couple different universities and industry partners as a part of the DARPA DSOC program. We're thankful to Tom Rondo for kind of getting us a little bit connected in with this community because it has some fun applications for us. And looking at who specifically was involved in preparing the content for this presentation, there's Serhan and myself, as well as Jacob, one of the heroes of the previous presentation as well, for his GNURadio expertise. So to give some motivation on what we're talking about today, the broad goal that we're working towards as a research group is to enable better use of heterogeneous systems. So everyone broadly knows that heterogeneous computation has a lot of potential in terms of the kinds of speedups you can theoretically gain if you're able to utilize these systems effectively and get the right kernels running on the right hardware at the right time. But it turns out that problem of actually doing that management is pretty difficult. So the approach that is taken in the program that we're working on is to look at these so-called domain-specific processors, which narrow the scope of the applications you're looking into to be narrow enough that you can effectively build accelerators for them, because you can't accelerate everything, but broad enough that those accelerators are useful, again, across multiple different types of workloads. And so what we're looking to do as a part of this program is to build a fairly usable domain-specific core-scale heterogeneous processor. And as a part of that, we focus on the runtime side of things. So you have the hardware design of the chip itself, and then you need some software layer on top to help you actually program and use applications on it. And so the solution we've come up with is a runtime we call CEDR. It's a compiler integrated extensible DSOC runtime. It's a runtime for general heterogeneous systems, not just the dash chip that we're building, that enables hardware agnostic application development, integration of new software and hardware scheduling policies to manage your hardware resources and task mappings. And then it allows for dispatching of tasks in the runtime to arbitrary hardware IPs that can potentially weren't known to your application at compile time. It's a fairly portable runtime, so it just runs in Linux user space, easy to port to generally, most other platforms. It runs as just a simple daemon process, and then as a part of our work, we've validated it at this point across lots of different FPGA and GPU setups on ARM, Arch64, and x86 systems. And we've found that it's pretty scalable. It supports, in theory, arbitrary mixtures of dynamically submitted workloads, all sharing the system. The broad overview is shown on the right-hand side of the screen here, with the left half of this picture being the compilation flow and the right half being the runtime. I'll go into the runtime a little bit more on the next slide, but just worth noting, if anyone is curious, the link for the sources for the source code is down at the bottom here, as well as a ACM transactions paper that we've published. So the runtime model itself is built around a core management thread that, as the name implies, manages the state of the system. So it essentially operates in a continuous loop of monitoring for incoming applications and launching them as necessary, waiting for tasks to be submitted by those applications, and then scheduling them with some user-defined scheduling heuristic. So that can be something simple like a round robin scheduler. That can be something more complex, an earliest task first, or a neural network based scheduling heuristic of some kind. But whatever path that task goes through, the way we represent schedulable resources in the system is by having this one worker thread per PE scheduling model. And this is something that broadly we've found in some previous discussions that it's, we believe it's still true, aligns with some of the goals of the GR 4.0 new schedule. But the way you schedule resources or tasks to resources is by pushing work into an input queue for the associated worker thread. And so a task might be a full FFT calculation or a full gem operation, things like that. And then the worker thread for that resource is either bound to the CPU that it represents. So if you're scheduling something to CPU 1, it goes to CPU 1. Or if you are dispatching to a dedicated FFT accelerator or GPU or something similar, then that worker thread takes on a different hat as a management CPU core that coordinates any of the data transactions that need to happen for that heterogeneous compute to actually get done. So on the right-hand side here, we just see an example of that for an FFT accelerator, where the management core configures maybe the FFT point size and whether it's a forward or inverse transform, configures the DMA engine to do the data streaming, and then waits for the task to come back. And then how you actually write applications for this runtime, we've gone through a few different approaches at this point, but what we've settled on for the moment is hardware agnostic API setup, which should be pretty familiar to most programmers. So the way that this ends up working is in your source code, you can write just some hardware agnostic kernel like FFT or gem or FIR like do a FIR filter. And at runtime, CEDR loads a compatible set of API implementations for the platform that you're running it on. The mechanics are that each of these APIs internally call into CEDR, which pushes a task into the ready queue that management thread oversees, and then over time, the management thread schedules and dispatches tasks to resources across the system. As tasks finish, they are reported as complete back to the user application, and the user app can just continue on its way. So with all of that background of this runtime out of the way, what did we do in this talk? The main goal of this presentation was to take some of these capabilities we've been building and see if we can leverage GNURadio applications and schedule them across heterogeneous platforms in the same way. So to do that, we built with the help of Jacob, an out-of-tree module that we call GRCder, hosted at the link down here. And the rough implementation approach is that blocks in GRCder make calls to CEDR APIs. And so these blocks can, of course, be used either directly in C++ GNURadio applications, or you can use them in flow graphs and convert to C++ with Python. And then when you run these flow graphs in CEDR, they have the effect of being dynamically scheduled and dispatched to any of the heterogeneous resources that you have available. And so we think that's a pretty powerful capability. A lot of other heterogeneous runtime approaches, you end up making these static decisions about where you're going to run code kind of at compile time. You know, someone analyzes the application and they go, oh, this part is the most suitable for GPU acceleration. We're going to run that on, we're going to put the CUDA call here and run it on GPU all the time. We find that if you want to have a world where you have a heterogeneous system actually sharing resources with other processes, you can't actually know what resource will be most efficient until you're you've made it to runtime, and you're making that decision based on the system state. And one other thing worth noting here is that these binaries are portable because we load the backend implementations in CEDR when you launch it at runtime. The binary of your application itself doesn't contain any of the implementation details of how those kernels are run. And so one example flow graph shown on the right here is just a demonstration we'd done on an FPGA system, a Xilinx CCU102. It had a couple of FFT accelerators and GEM accelerators. And we have one GNURadio radar correlator application sharing the system with two non-GNURadio applications of Wi-Fi transmit and synthetic aperture radar. They are being injected periodically. With the first portion of the flow of the Gantt chart we see here shown on the left, we see all three applications sharing the resources and at runtime. And then there's a middle portion where only the GNURadio application is running. And then in the third phase, the Wi-Fi transmit comes back in and is able to share effectively. So we won't see this demo live, but in a few minutes, Serhan will be showing similar capabilities on the Jetson GPU development board. But before we get to that, we'll talk about the demo that he'll be going through. So the goal here is to show dynamic heterogeneous scheduling of GNURadio blocks in CEDR. So to do that, we're just going to run a simple correlator application with and without GPU acceleration on an NVIDIA Jetson AGX Xavier dev board. And then we will just monitor the waterfalls generated from both the standalone typical GNURadio flow and the CEDR-based execution to verify that it's correct. And then we'll see that the tasks on the GPU were being dynamically allocated that way. So with that, we will go over to the other board.
Is it good? Okay. First, we will set the environment, and this will build CEDR and install every API call and it will also build the integration with GNURadio and also build the install that integrated GNURadio blocks that use CEDR APIs, and then we will look at our application's CEDR version, where we are using the CEDR blocks for FFTs. And here, these are our FFT blocks that basically uses the CEDR FFTs that will be scheduled in runtime. And this application in standalone GNURadio is looking like this. We use only the regular FFTs for the GNURadio from GNURadio. And then we need to compile this application that uses the CEDR APIs. We first generate the Python code, and then from here we compile it. We first convert it to C and then create the shared objects that we are going to use in CEDR. Here we see the shared object. Let's go to the build directory of CEDR and copy the shared object here. Now we have the shared object. Now we will run CEDR here. And on the second terminal, we will submit the application we just created. And at the same time, I will also run the GNURadio standalone CEDR, standalone application. The right one should have shown the CEDR's execution.
So I think we're going to try and relaunch that flow graph there.
Yeah.
Okay. And then so from there we can see the two different implementations running side by side. The one on the right is running in CEDR, a little bit slower because we have a debug build and a lot of logging enabled to collect metrics about the application going on. But a lot of those metrics can then, you can turn around and use those for things like training data for neural network or imitation learning based schedulers.
Now this one was only using CPU. Now let's kill this one. Run the plot.
And so just to show basic functionality, we had started just with a CPU validation that we're able to just port an application to run on CPU and CEDR at all. And now Serhana is going to go ahead and do the CUDA-enabled build. And we'll see the GPU acceleration there. Okay.
This time on the right, it's using GPU also together with the CPUs.
And it's worth noting that that was still the same flow graph as we had been using previously, just running in CEDR loaded with a different configuration. And now just to really convince ourselves that this actually did run on GPU, we can look at the CEDR scheduling logs to see where all of the tasks were dispatched and check that some of them actually did end up there.
So here we see that some of the FFTs were scheduled on the CPU and some of them were scheduled on the GPU, and this is decided on the runtime. Go back to the slides.
And with that, that's the end of the live demo here. Going back to the slides, just to show a quick summary. Okay, so yeah, we've shown CEDR, a name that maybe you're tired of hearing me say by now, and showed that it's a a runtime for Linux-based heterogeneous systems, along with a proof of concept out of tree module that shows how to integrate GNURadio applications into our runtime. Some future directions. Right now, that out of tree module only has the FFT block, so adding more blocks within that would be nice in the future. And alongside this, we would love to continue working with the community to see what opportunities there are for incorporating this in the GR 4.0 new schedule work. But with that, we'll end the talk here and see if anyone has any questions.
Do you have a question, or are you just lifting your hand? I don't think you have a question. There we are.
So a big gotcha with heterogeneous computing is timing. And you say offload the data, and then you just sit there and wait for it to come back. And so yes, you're using less CPU, but you're not actually processing anything any faster. Or you just keep sending data off and you overrun buffers, or you have other problems. So does CEDR do anything to help the programmer make good choices for offloading and waiting?
I think the power that it gives is it lets you test out different scenarios and see what works in your use case pretty trivially. So it's not difficult to implement maybe a CPU only scheduler or a scheduler that tests out different scenarios and allows you to do that kind of trade analysis. The exact specifics of how to handle efficient data transfer do, I think, vary based on the platform you're running on. And so we don't have a completely abstracted answer for that, but that could be something along the lines of, I know there's been zero copy buffer work presented in the past, or removing the double copy problem, things like that, that could potentially be integrated as potential approaches to solve this.
Do any more questions? Okay, I have a question. So one thing I didn't fully understand in your demo is, like, what is the actual input to the scheduler? Is it like the entire flow graph, and then it picks out the individual blocks that can be shuffled around?
It would be individual tasks. So one task might be a full FFT call, but each time the GNURadio block's work function is called, that pushes a new FFT into the queue for CEDR to schedule.
Okay. So there's basically a hook that figures out when those tasks are being called.
Yeah, that's somewhat on the bottom right-hand side of this plot. The dash FFT that is in the user application is roughly equivalent to initializing a pthread barrier and then sending this in queue kernel is a magic function that links within CEDR to push a task to the ready queue with all of the necessary arguments. And then the user application waits for completion, or we have non-blocking APIs that if you know something is independent, you want to run things in parallel, that's an option as well. But.
Okay, but the GNURadio 3 scheduler is still running then, and then I'm curious if you do it like that, are you like gonna have like some weird effects of like the TBB scheduler and your task dispatcher like fighting each other or like stepping on each other's toes or something like that?
I think there's definitely opportunities for that, particularly given the way that all of these worker threads we are setting their affinities manually in ways that may somewhat conflict with how. I mean, it's ultimately the kernel scheduler still scheduling threads at the end of the day for us at the moment. So I think there's some opportunity. There probably are some possible ways that could conflict, but I don't think we've explored this integration enough to really say what those are.
Okay. But I mean, you've mentioned GNURadio 4, and I think that's where we can see more like opportunities to employ something like that rather than GNURadio 3. We have time for one more question, I think. Oh, there's one over there. Perfect. Let me just walk over.
I so apologize if I'm not up on some of the lingo, but I'm wondering how the scheduler kind of decides what to do at runtime. Like, if a task is submitted, is it figuring out how long that task would take on all the different architectures, or is it just like submitting it to the first thing that's open, right? Like, I guess I'm wondering, like, how does it know to submit it to a GPU? Does it know that that's going to be faster per se on the GPU, given all the overhead, for example?
That depends on the algorithm chosen, I guess. So when you launch CEDR, you choose which particular scheduling algorithm you want to use. You can just use, we call the simple scheduler is a round robin approach, and it just goes through the entire list of resources and attempts to find something compatible with the task you have, because there's also chances that you have a gem task and a round robin would try and put it on an FFT accelerator, and it goes, no, that's not compatible, so it moves on. But there's a lot of opportunity for design of more intelligent heuristics, and we have some details of that in the paper in terms of work from our collaborator at UW at Wisconsin in doing an imitation learning based scheduler of a more complex kind of smarter policy, but using imitation learning to lower the runtime complexity so that it also meets real-time needs.